The discovery happens on a night like countless others. Automated telescopes sweep across predetermined sections of sky, their sensors converting photons into digital signals, their algorithms searching for movement against the fixed background of distant stars. Most objects appear exactly where celestial mechanics predicts they should be. Asteroids tracing ellipses around the sun, planets following their ancient grooves through space, moons keeping time with gravitational precision. But on this particular night, in images captured hours apart, one point of light sits where no catalogue places it. The position is wrong. The movement is wrong. Something is approaching from an angle that makes no sense within the architecture of our solar system. At first, the assumption follows established patterns. Perhaps a new asteroid, previously undetected, following an eccentric orbit that carries it far from the sun before swinging back inward. Perhaps a comet from the Oort cloud, that distant reservoir of icy bodies surrounding our star, like a spherical halo extending nearly a light-year into space. The object receives a provisional designation, a string of numbers and letters that will change once its orbit becomes clear. Astronomers request follow-up observations. More telescopes turn toward that small patch of sky. The measurements accumulate slowly. Position at 1 hour, position at 3 hours, position the following night. Each data point refines the trajectory, narrows the possibilities, constrains the mathematics. Orbital determination requires patience. The object must move far enough across the sky for its path to reveal itself with statistical confidence. And as the observations multiply, as the orbital elements begin to converge towards stable values, one parameter emerges that changes everything: the eccentricity. In orbital mechanics, eccentricity measures the shape of a path through space. 0 describes a perfect circle. Values between 0 and 1 describe ellipses of varying elongation, the orbits of planets, asteroids, comets bound to the sun by gravity's patient grip. A value of exactly 1 traces a parabola, the boundary case between captivity and escape. But 3I/Atlas, as the calculations sharpen, shows an eccentricity greater than 1. The number sits comfortably above that threshold, beyond the realm of statistical uncertainty. The orbit is hyperbolic. This single fact contains profound implications. A hyperbolic trajectory means the object is not bound to the sun. It arrived from elsewhere, fell briefly through our system's gravitational influence, and will depart again into interstellar space. The velocity confirms what the eccentricity suggests. 3I/Atlas moves too fast for our star to capture it, carries too much kinetic energy to settle into a closed orbit. Only took 4.5 billion years for our solar system to receive a visitor from beyond its borders that humanity actually noticed. The realization spreads through astronomical communities with quiet intensity. This is only the 3rd confirmed interstellar object detected passing through our solar system, hence the designation 3 Hua, marking its place in that exclusive catalogue. The first? Umuma arrived in 2017, a tumbling enigma that departed before thorough observation became possible. The second, 2I/Borisov, appeared in 2019, revealing the familiar anatomy of a comet despite its exotic origin. Now 3I/Atlas joins that sparse list. Another messenger from the space between stars. What remains uncertain is how long such objects have been passing through undetected. Statistical models, extrapolating from the handful of discoveries, suggest perhaps 1 or 2 interstellar visitors cross the inner solar system every year, most too small, too distant, or too faint for current surveys to notice. Earth orbits within a river of cosmic traffic that only recently became visible to human instruments. The galaxy exchanges material constantly, stars sharing the debris of their formation across light years of apparent emptiness. The early observations establish basic facts. 3I/Atlas appears comet-like, Not asteroid-like, it develops a visible coma as solar radiation warms its surface, releasing gases that glow softly in reflected sunlight. The nucleus itself, the solid body beneath that expanding envelope, measures perhaps a few hundred meters across, though estimating the size of distant comets remains imprecise. It brightens as it approaches the Sun, following the predictable pattern of sublimation-driven activity. In these respects, it resembles solar system comets, suggesting similar formation processes, similar composition, similar physics operating in whatever stellar system gave it birth. But one detail sets it apart absolutely: the trajectory that will carry it away forever. Solar system comets may venture far from the Sun, may spend millennia in the darkness beyond Neptune, but gravity eventually draws them back. The ellipse closes, the cycle repeats. 3I/Atlas traces no such closed curve. Its path bends around our star like light bending through a lens, deflected but not captured, moving through and onward. After this single passage, after this brief illumination, it will fade back into interstellar darkness, continuing a journey that may span millions of years before encountering another star. Astronomers calculate the geometry with increasing precision. The closest approach to the Sun perihelion will occur at a distance safely beyond Earth's orbit, ensuring the comet remains faint but observable for weeks or months. The angle of approach, the tilt of its trajectory relative to the solar system's ecliptic plane, the direction from which it came, all these parameters narrow down with each new measurement. And from these numbers, questions begin to form. Where did it originate? How long has it been travelling? What can its composition reveal about planet formation elsewhere in the galaxy? The telescopes continue watching. The data continues accumulating. And somewhere between Mars and Jupiter, a visitor from unimaginable distance crosses through our small neighbourhood of space, indifferent to the attention it receives, following physics older than worlds. The mathematics of orbital motion reduce all trajectories to elegant equations. Given a position and velocity at any moment, given the mass of the Sun and the inverse square law of gravitation, the entire path through space becomes calculable past, present, and future locked into geometric certainty. For objects bound to the solar system, these calculations yield ellipses of various shapes and orientations, closed curves that repeat endlessly unless perturbed by planetary encounters. But for 3I/Atlas, the equations trace something fundamentally different, a hyperbola that opened somewhere in interstellar space and will close again in interstellar space, with our Sun merely a focal point briefly bending the path. The orbital elements tell the story in precise numerical language. The semi-major axis, that parameter defining the size of elliptical orbits, becomes negative for hyperbolic trajectories, a mathematical signal that no closed orbit exists. The eccentricity measures approximately 1.2 comfortably beyond the threshold of gravitational binding. The inclination shows the comet approaching from well above the ecliptic plane, descending through the solar system at an angle that native objects rarely achieve, and the velocity at infinity the speed 3I/Atlas would possess infinitely far from the Sun's influence, calculates to roughly 15 kilometers per second relative to the local standard of rest. This last value proves particularly revealing. The local standard of rest represents the average motion of stars in our galactic neighbourhood, a kind of cosmic background against which individual stellar velocities can be measured. That 3I/Atlas moves at 15 kilometers per second relative to this reference frame suggests it has been travelling through interstellar space for a very long time. Long enough for whatever initial velocity it possessed when ejected from its birth system to have been modified by countless small gravitational interactions with passing stars, by the gentle tug of the galaxy's spiral arms, by the accumulated influence of deep time. Astronomers work backward through the trajectory, tracing the comet's path into the past. Given its current position and velocity, given the Sun's gravitational influence subtracted from the calculation. Where was 3I/Atlas 100 years ago, 1,000 years ago, a million? The precision degrades rapidly with temporal distance. Tiny uncertainties in current measurements compound exponentially when projected backward across centuries. But the general direction remains clear. The comet approached from the general region of the constellation Ursa Major, descending toward the solar system from the galactic north at an angle that suggests no recent close encounter with nearby stars. The nearest stellar system in that rough direction lies over 4 light-years distant, but 3I/Atlas likely did not originate from our immediate stellar neighbours. Its velocity and trajectory show no obvious connection to any specific star currently near the Sun. Instead, it probably wandered for millions of years, perhaps tens of millions, gradually crossing the light years between its birthplace and our system. The galaxy rotates with patient slowness. Stars drift through the spiral arms, their positions relative to one another constantly shifting. Whatever stellar system formed 3I/Atlas may now lie on the opposite side of the galactic disk, or may have long since exhausted its fuel and collapsed into stellar remnant. The hyperbolic excess velocity that 15 kilometers per second measured at effective infinity also places constraints on the ejection mechanism that sent the comet into interstellar space. Comets in our own solar system occasionally achieve escape velocity through gravitational assists during close encounters with Jupiter or other giant planets. A comet falling deep into Jupiter's gravity well can emerge with enough added velocity to break free from the Sun entirely, slingshot out into the galaxy. Similar processes likely operate around other stars. 3I/Atlas probably originated in a planetary system analogous to ours, formed in the outer regions where volatiles remain frozen, then scattered inward by gravitational perturbations until a close encounter with a massive planet accelerated it beyond escape velocity. Only took one unlucky pass, one specific geometric alignment, to transform a stable solar orbit into an eternal exile. The probability of such an event for any individual comet remains extremely low, but given billions of comets orbiting billions of stars across billions of years, the galaxy fills gradually with these ejected wanderers. Current estimates suggest trillions of interstellar comets drift through the Milky Way, the accumulated debris of planetary systems across galactic history. Most will never encounter another star closely enough to be perturbed from their paths. They simply travel, frozen and dark, through the vast spaces between stellar systems. What remains mysterious is the exact formation environment that produced 3I/Atlas. Did it assemble in a disk around a star similar to our Sun, around a red dwarf? Those small cool stars that constitute the majority of stellar population, around a binary system where 2 stars orbit each other, their combined gravity sculpting unusual planetary architectures. The comet's composition will offer clues, but ambiguity persists. Planet formation follows universal physical principles: gravity, thermodynamics, chemistry, but local conditions vary. Temperature gradients in protoplanetary disks determine which volatiles condense at which distances. Stellar luminosity affects the snow line, that boundary beyond which water ice remains stable. The presence or absence of giant planets influences how material migrates through the disk. These variables produce family resemblances but not identical outcomes. 3I/Atlas may resemble solar system comets in broad composition, while differing in specific isotopic ratios, in the precise mixture of ices, in trace elements incorporated during formation. Or it may prove nearly indistinguishable, evidence that planet formation proceeds similarly regardless of stellar specifics. The observations required to answer these questions take time, require large telescopes, demand careful spectroscopic analysis. The trajectory itself offers one final irony. 3I/Atlas will depart the solar system travelling in a different direction than it arrived. deflected by the sun's gravity through a predictable angle. The hyperbola bends, curves around the focal point, redirects the comet's path without capturing it. Millions of years from now, if 3I/Atlas encounters another stellar system, observers there might trace its trajectory backward and find it pointing vaguely toward our sun, but by then the sun will have moved, the galaxy rotated, the geometric relationship dissolved into meaninglessness. Interstellar space erases trajectories given enough time. Only the journey itself persists, silent and slow. The orbital elements sit in databases now, refined to high precision. The path is known, the future is calculable. And yet the questions multiply faster than answers accumulate. The journey begins in darkness. Not the darkness of night on Earth, where atmosphere scatters sunlight and moonlight and the glow of distant cities, but the absolute darkness of interstellar space, where the nearest star appears as a point of light no brighter than Venus seen from Earth, and all other stars remain fixed and distant, their light taking years or centuries to cross the void. 3I/Atlas drifts through this darkness for timescales that dwarf human civilization, for timescales that approach the age of complex life on Earth, moving at 15 kilometers every second through emptiness so complete that a single hydrogen atom per cubic centimeter constitutes relatively dense environment. The distance between stars defies comfortable comprehension. The nearest star to our sun lies 4.24 light-years away, a gap so vast that light, travelling at 300,000 kilometers per second, requires over 4 years to cross it. At 3I/Atlas's velocity of 15 kilometers per second, covering that same distance would require roughly 85,000 years. But the comet likely travelled much farther than the nearest stellar neighbour. If its origin lies 10 light-years distant, the journey spans 200,000 years. If 20 light-years, then 400,000 years. If 50 light-years, well within the galaxy's local stellar neighbourhood, then 1,000,000 years of silent travel through space so empty that meaningful encounters approach impossibility. During this crossing, the comet experiences conditions unlike anything found within planetary systems. The temperature of the comet's surface equilibrates with the cosmic microwave background, that faint radiation left over from the Big Bang, warming all of space to approximately 2.7 degrees Kelvin above absolute zero. At such temperatures, molecular motion nearly ceases, water ice becomes harder than steel. Volatiles that would readily sublimate in sunlight remain locked in solid phase, their molecules vibrating minimally in crystalline lattices. The comet is a frozen archive, its chemistry suspended, its structure preserved in cryogenic stasis. The radiation environment differs profoundly from conditions near stars. Cosmic rays, high-energy particles accelerated to near light speed by supernovae, by pulsars, by the galaxy's magnetic fields constantly bombard the comet's surface. These particles penetrate several meters into the ice, breaking chemical bonds, creating new compounds through radiolysis, darkening the surface as complex organic molecules polymerize into tarry residues. Over millions of years, this cosmic ray weathering alters the outer layers of the nucleus, creating a rind of processed material distinct from the pristine interior. Only took a few million years to erase all record of the comet's original surface appearance. Impacts remain possible even in interstellar space, though extraordinarily rare. The comet travels through the local interstellar medium, that tenuous gas pervading the space between stars, mostly hydrogen and helium, with trace amounts of heavier elements. At 15 kilometers per second, even individual atoms striking the surface carry significant kinetic energy. Larger dust grains, themselves adrift in the galaxy, occasionally collide with the comet at relative velocities that vaporize both projectile and target material. These micrometeorite impacts occur perhaps once per century, leaving tiny craters invisible to distant observation, but gradually roughening the surface texture over geological time. The comet also passes through the galaxy's magnetic field, that tangled web of field lines threading through interstellar space, shaped by stellar winds and supernova shocks and the rotation of the galactic disk itself. Charged particles trapped in this field spiral along field lines, creating currents that extend across light years. 3I/Atlas, being electrically neutral overall, responds only weakly to these fields, but any ionized material on its surface or in its immediate vicinity follows the field's guidance, potentially stripping away atoms one by one over immense durations. What remains uncertain is whether the comet's interior has remained pristine or whether cosmic rays have penetrated deeply enough to alter chemistry throughout the nucleus. Laboratory experiments suggest that radiation processing can affect material to depths of several meters, creating new molecules, destroying old ones, redistributing elements. But the exact effects depend on the comet's composition, its density, its initial chemistry variables that remain unknown until spectroscopic analysis reveals what volatiles emerge when solar heating finally warms the surface. The trajectory during interstellar travel follows nearly a straight line, with no significant gravitational sources nearby, no planets to perturb its path, no stellar radiation to create asymmetric outgassing forces. 3I/Atlas simply continues in whatever direction its ejection from the origin system imparted. The galaxy's gravity influences the path over very long time. Scales stars orbiting the galactic center follow curved paths, gradually spiraling inward or outward depending on their velocities. But for a million-year journey, for even 10 million years, the deviation from a straight line remains small. The comet aimed at our solar system long before Earth's current ice age began, before Homo sapiens emerged, before the Himalayan mountains finished their slow collision-driven rise. Occasionally, though rarely, the comet passes within a few light-years of other stellar systems. These distant encounters exert minimal gravitational influence, not enough to significantly alter the trajectory, not enough to capture the comet into orbit, but enough to deflect the path by tiny fractions of a degree. Accumulated over many such encounters, these deflections blur the connection between the comet's current trajectory and its origin point. Tracing the path backward becomes increasingly speculative with each additional million years, each possible stellar passage adding uncertainty. The isolation during this crossing approaches completeness. No worlds orbit nearby, no moons reflect distant starlight, no asteroid belts mark the boundary between rocky and gaseous planet formation. The comet travels alone, its only companions the stars themselves, fixed and distant, their patterns shifting infinitesimally as the comet's motion changes perspective. The constellation shapes familiar from Earth Orion, Ursa Major, Cassiopeia gradually distort as viewed from the comet's wandering frame of reference, stars in the foreground appearing to drift relative to background stars, the three-dimensional structure of the galaxy revealing itself through parallax. And yet the journey continues, patient and inevitable. The comet falling through the galaxy's gravitational landscape like a marble rolling across an imperceptibly tilted floor. 15 kilometers per second, 13 astronomical units per year, 1 light year every 20,000 years. The numbers describe motion almost too slow to matter on galactic scales, almost too fast to comprehend on human scales. And somewhere ahead, still invisible, still years or decades or centuries distant depending on the specific trajectory, a particular yellow star begins to brighten, its gravity well deepening as distance decreases, its light slowly intensifying from anonymous point to notable beacon. The crossing nears its end, though the comet itself registers nothing, knows nothing, simply continues. The nucleus of 3A/Atlas measures perhaps 300 meters across, though exact dimensions remain difficult to determine at such distances, irregular in shape. Like most comets, no sphere here, no geometric perfection, but rather a lumpy aggregate of frozen material held together by its own feeble gravity and the sintering of ice over millions of years. The surface appears dark, nearly black, reflecting only a small percentage of incident light. This low albedo characterizes most cometary nuclei, their surfaces darkened by organic compounds polymerized through radiation exposure, through thermal cycling during previous passages near stars, through the accumulated chemistry of deep time. Beneath that darkened crust lies the comet's true substance. Water ice dominates the composition, as it does for most comets regardless of origin. Hydrogen and oxygen, the first and third most abundant elements in the universe, combine readily into H2O molecules in the cold outer regions of protoplanetary disks. When temperatures drop below approximately 150 Kelvin, water vapor condenses into ice crystals that accumulate into larger bodies through gentle collisions, through electrostatic attraction, through the patient work of gravity operating on timescales spanning millions of years. The ice in 3I/Atlas formed this way, grain by grain, in orbit around a star whose light the comet has not felt for geological ages. But water ice alone does not constitute a comet, mixed throughout the nucleus, frozen into the ice matrix or existing as separate inclusions. Other volatiles contribute to the composition. Carbon monoxide ice, freezing at even lower temperatures than water, likely condensed further from the origin star, then migrated inward through disk dynamics or became incorporated into the comet during scattering events. Carbon dioxide, another common volatile, freezes readily at the temperatures characteristic of outer planetary systems. Methane, ammonia, molecular nitrogen, all these simple molecules appear in varying abundances depending on the specific thermal and chemical history of the formation environment. The exact ratios between these ices carry information about conditions in the protoplanetary disk where 3I/Atlas assembled. Temperature gradients determine which volatiles remain gaseous and which condense into solid form at any given distance from the star. A comet forming very far from its star, in the coldest regions of the disk, might incorporate significant amounts of carbon monoxide and nitrogen volatiles that require extremely low temperatures to freeze. A comet forming closer in, where temperatures permit only water and carbon dioxide to condense, would show a different compositional signature. When 3I/Atlas begins outgassing as it approaches the Sun, spectrometers will measure these ratios, comparing them to solar system comets, searching for similarities or differences that constrain formation conditions embedded within the ice matrix. Silicate dust grains provide the comet's rocky component. These microscopic particles formed in the hot inner regions of the protoplanetary disk, where temperatures permitted the condensation of refractory minerals that remained solid even at high temperatures. Radiation pressure and turbulent mixing in the disk transported these grains outward, into the cold zones where ice condensation occurs, allowing them to become incorporated into growing cometary bodies. The dust grains in 3I/Atlas likely resemble those found in solar system comets olivine, pyroxene, amorphous silicates, perhaps some crystalline materials that formed at high temperatures and somehow survived transport to the outer disk. Iron and other metals exist in trace amounts, either as pure metallic grains or as components within silicate minerals. The exact abundances depend on the chemical composition of the origin star's protoplanetary disk, which in turn depends on the mix of elements inherited from previous generations of stars. Stars forming in regions enriched by recent supernovae incorporate more heavy elements into their planetary systems. Stars forming from relatively pristine gas show lower metallicities. These differences appear subtle but measurable, potentially distinguishing between comets from different galactic environments. What remains mysterious is whether 3I/Atlas contains organic molecules more complex than simple ices. Comets in our solar system harbour impressive chemical inventories, amino acids, polycyclic aromatic hydrocarbons, complex carbon chains approaching biological relevance. These molecules form through multiple pathways, some condense directly from the gas phase in the protoplanetary disk. Some form on grain surfaces through surface chemistry catalyzed by ultraviolet radiation. Some result from radiation processing during interstellar travel. Laboratory experiments recreating likely formation conditions produce startlingly complex chemistry from simple starting materials, suggesting that comets universally serve as repositories for prebiotic molecules. The nucleus likely contains crystalline ice and amorphous ice in varying proportions. Amorphous ice forms when water vapor condenses very rapidly at extremely low temperatures, creating a disordered solid structure lacking the regular lattice of crystalline ice. Over time, at temperatures above approximately 130 Kelvin, amorphous ice transitions to crystalline form, releasing stored energy in the process. This phase transition may contribute to cometary activity, providing an internal heat source that drives outgassing even at large distances from the Sun. Whether 3I/Atlas retains any amorphous ice after millions of years of cosmic ray bombardment remains uncertain. The radiation gradually converts amorphous regions to crystalline structure through molecular rearrangement. Porosity characterizes the internal structure. Comets are not solid blocks of ice, but rather loose aggregates. Their interiors shot through with void spaces. Their effective density is much lower than pure ice. The porous structure results from the gentle accretion process that built the nucleus, with ice grains settling together under weak gravity, creating a network of empty spaces between consolidated regions. Porosities can reach 70 or 80%, meaning most of the comet's volume contains vacuum rather than solid material. Only took a few million years of patient accumulation to build such delicate architecture. The layering within the nucleus may record the comet's formation history. If the comet accreted material gradually as it migrated through different regions of the protoplanetary disk, each layer might show slightly different composition, reflecting the local conditions where that layer formed. Alternatively, if the comet formed rapidly from the collapse of a small region within the disk, the composition might remain relatively homogeneous throughout. Impacts during the comet's history could have mixed the layers, erasing primordial structure and creating a jumbled interior. Without drilling into the nucleus or observing it fragment naturally, determining the internal structure remains speculative. Temperature governs everything now. As 3I/Atlas approaches the Sun, as solar radiation begins to warm the surface, the dormant chemistry awakens. Ice sublimates, transitions directly from solid to gas without passing through liquid phase. The gases expand outward, carrying dust grains loosened from the ice matrix, creating the visible coma that first alerted astronomers to the comet's presence. The transformation from inert ice ball to active comet follows thermodynamic inevitability, the warmth unlocking volatiles frozen since formation, releasing them into space where instruments wait to measure their composition. The nucleus itself remains hidden beneath the expanding gas cloud, but its nature determines everything that follows. The awakening begins subtly, at distances beyond Jupiter's orbit, where sunlight carries little warmth. The comet's surface remains frozen and inert. But as 3I/Atlas continues its inward trajectory, as the distance to the Sun decreases and the inverse square law dictates steadily increasing solar flux, the surface temperature rises degree by degree. At first, nothing visible changes. The nucleus continues tumbling through space, dark and silent, its rotation inherited from whatever collisions shaped its angular momentum millions of years ago. But molecular motion within the ice lattice accelerates, vibrations increase. The transition from absolute dormancy to subtle activity crosses no sharp threshold. It emerges gradually, probabilistically, as increasing numbers of molecules achieve escape velocity from the ice matrix. Water ice begins sublimating significantly when surface temperatures exceed approximately 200 Kelvin, though the exact threshold depends on pressure, on ice structure, on the presence of other volatiles mixed into the matrix. As solar heating pushes surface temperatures above this limit, water molecules break free from the solid phase, emerging as vapor that expands rapidly into the surrounding vacuum. The process requires energy, the latent heat of sublimation, approximately 2800 joules per gram for water ice, which the ice absorbs from incoming sunlight. This energy absorption cools the surface slightly, creating a negative feedback that moderates the sublimation rate. Only took 4.5 billion years for thermodynamics to remain thermodynamics. But water is not the first volatile to emerge. More volatile ice is carbon monoxide, carbon dioxide. Methane sublimate at lower temperatures, beginning their outgassing while the comet still cruises through the outer solar system. These supervolatile compounds create the initial coma, that tenuous envelope of gas expanding around the nucleus. At first, the coma remains invisible to human observers, too faint and diffuse to reflect enough sunlight for detection. But as the sublimation rate increases, as more molecules escape the nucleus every second, the coma brightens and expands, eventually becoming visible to ground-based telescopes as a fuzzy patch surrounding the stellar point of the nucleus. The expansion follows simple physics. Gas molecules sublimating from the surface possess thermal velocities determined by temperature, typically a few hundred meters per second, for the relevant molecular masses and temperatures. In the vacuum of space, with no atmosphere to resist their motion, these molecules simply continue outward in straight lines, rarely colliding with other molecules in the increasingly diffuse coma. The gas density drops rapidly with distance from the nucleus, following an inverse square relationship. At distances of a few hundred kilometers, the coma becomes so tenuous that molecular collisions essentially cease, and the expanding gas enters what's called the collisionless regime, where individual molecules travel ballistically outward. Dust grains entrained in the sublimating gas add visual prominence to the coma. As ice sublimates from the surface, dust particles previously embedded in the ice matrix lose their mechanical support and lift off, carried outward by the expanding gas through momentum transfer. The size distribution of these particles spans orders of magnitude from submicron grains barely larger than large molecules to millimeter-sized pebbles, whose release requires stronger gas flows. The smallest grains, once liberated, respond strongly to solar radiation pressure, that gentle but persistent force exerted by photons striking small particles. Radiation pressure accelerates these grains away from the sun, creating the characteristic dust tail that can extend millions of kilometers behind the comet. Larger dust grains, less affected by radiation pressure, follow trajectories determined primarily by the comet's orbital motion. They spread out along the comet's path, creating a second tail, the Sindine tail, that curves gently as the grains respond to both solar gravity and radiation pressure. The exact morphology of the dust tails encodes information about the size distribution of released particles, about the timing and intensity of outgassing events, about the rotation state of the nucleus. Careful modelling of tail structure allows astronomers to reconstruct the history of dust release spanning weeks or months. What remains mysterious is the exact geometry of the outgassing. Cometary nuclei do not sublimate uniformly across their surfaces. Shadowed regions remain cold. Areas covered by thick dust mantles insulate underlying ice from solar heating. Variations in composition create patches of ice with different sublimation temperatures. The result is that outgassing often concentrates in localized jets, discrete streams of gas and dust erupting from specific active areas, while the rest of the surface remains relatively quiet. These jets create asymmetric forces on the nucleus, altering its rotation state over time, potentially causing the comet to spin faster or slower, to tumble chaotically or settle into stable rotation. The coma itself becomes a temporary atmosphere, albeit one that continuously escapes into space. Near the nucleus, where gas density remains relatively high, molecules collide frequently enough to establish a local temperature through thermalization. This region, called the collision sphere or collisionopause, extends perhaps a few hundred kilometers from the nucleus for a moderately active comet. Beyond this boundary, in the collisionous regime, the concept of temperature becomes less meaningful. Molecules simply fly outward with whatever velocity they possessed when they escape the nucleus. Ultraviolet sunlight dissociates many of the sublimating molecules, breaking them into fragments that emit characteristic fluorescence. Water molecules photodissociate into hydroxyl radicals and hydrogen atoms, carbon dioxide fragments into carbon monoxide and atomic oxygen. These daughter products create their own emission signatures, glowing at specific wavelengths as excited electrons return to lower energy states. The coma becomes a fluorescent cloud, its spectrum revealing the composition of the parent molecules sublimating from the nucleus. Only took a few million kilometers of approach for the transformation from invisible traveler to glowing beacon. The hydrogen atoms produced by water photodissociation deserve special attention. Being extremely light, hydrogen atoms move very fast once released several kilometers per second. They escape the coma entirely, creating an enormous hydrogen cloud surrounding the comet, sometimes extending millions of kilometers in all directions. This hydrogen envelope remains invisible to optical telescopes but glows brightly in ultraviolet wavelengths, creating a vast glowing sphere that dwarfs the visible coma. Space-based ultraviolet telescopes reveal these hydrogen clouds, measuring their extent and brightness to estimate total water production rates. The production rate, the mass of material sublimating from the nucleus per unit time, varies with heliocentric distance, with solar illumination angle, with the comet's rotation bringing different surface regions into and out of sunlight. For 3I/Atlas, peak activity likely occurs near perihelion, when solar heating reaches its maximum intensity. Production rates for moderately active comets can reach hundreds of kilograms per second at perihelion, millions of kilograms per day, enough mass loss over a single passage to measurably reduce the nucleus's mass and alter its surface topography. The coma expands outward, patient and inevitable, carrying information about the comet's composition into the realm where spectrometers can analyze it, where chemistry frozen for millions of years finally reveals itself to distant observers. Light carries information. Photons from the sun strike molecules in the expanding coma, and those molecules respond according to quantum mechanical principles governing electronic transitions, vibrational modes, rotational states. Each molecular species absorbs and emits light at characteristic wavelengths determined by its internal structure, the arrangement of atoms, the strength of chemical bonds, the masses of constituent nuclei. Water molecules resonate at different wavelengths than carbon dioxide molecules, which differ from carbon monoxide, which differ from methane, cyanide, ammonia, and the dozens of other species potentially present in cometary outgassing. By dispersing the comet's light into its component wavelengths by obtaining spectra, astronomers decode the chemical composition without ever touching the physical material. Spectrometers mounted on large telescopes collect photons from 3I/Atlas's coma and separate them by wavelength with diffraction gratings or prisms. The resulting spectrum shows brightness as a function of wavelength, revealing patterns of absorption and emission that serve as molecular fingerprints. In the visible and near-infrared portions of the spectrum, emission bands from common radicals dominate the distinctive green glow of diatomic carbon at 514 nanometers, the cyan emission from the CN radical near 388 nanometers. The red bands of ionized water at 619 nanometers. Each emission feature corresponds to specific electronic transitions in molecules energized by solar ultraviolet radiation. Water production receives particular attention because water constitutes the dominant volatile in most comets. Direct detection of water vapor proves challenging in visible wavelengths. Water's strongest emission features lie in the infrared and ultraviolet, but the hydroxyl radical OH serves as an excellent proxy. Every water molecule photodissociating under solar UV produces one OH radical, which emits strongly at 308 nanometers. By measuring the brightness of this OH emission and applying models for the photodissociation rate and coma expansion, astronomers calculate the water production rate, how many water molecules escape the nucleus per second, how much ice sublimates per day, how rapidly the comet loses mass during its solar passage. For 3I/Atlas, early spectroscopic observations detect the expected hydroxyl emission, confirming significant water content. The measured production rates evolve as the comet approaches perihelion, increasing as solar heating intensifies. Following power law relationships between heliocentric distance and sublimation rate that characterize most comets, the numbers suggest water dominates the volatile inventory, consistent with formation in a cold protoplanetary disk where water ice condensed readily. Only took a few photons per second arriving at Earth's telescopes to reveal composition across light years of distance. But water is not the only story. Carbon monoxide emission appears in infrared spectra, detected through its fundamental vibrational band near 4.7 micrometers. The CO production rate relative to water, the CO-H2O ratio, provides constraints on formation temperature. Carbon monoxide ice requires colder conditions to condense than water ice, so comets rich in CO likely formed farther from their parent stars or incorporated material from the coldest regions of their protoplanetary disks. The measured CO-H2O ratio for 3Y/Atlas falls within the range observed for solar system comets, suggesting similar thermal histories, similar formation distances scaled to the luminosity of their respective parent stars. Carbon dioxide also makes its presence known through infrared emission bands and through visible emission from ionized CO2+ in the coma. The relative abundance of CO2 to water offers additional formation constraints. Some models suggest CO2 forms primarily through surface chemistry on icy grains, rather than through direct condensation from the gas phase, meaning its abundance depends on grain surface areas, on residence times in the disk, on the efficiency of catalytic reactions. The exact mechanisms remain debated, but comparative measurements across many comets gradually build an empirical understanding of which volatiles correlate with one another, which ratios remain relatively constant, which vary widely, suggesting diverse formation conditions. What remains mysterious is whether 3I/Atlas shows any compositional signatures definitively distinguishing it from solar system comets. Early measurements suggest broad similarity. Water dominates. Carbon-bearing volatiles appear in familiar ratios. The spectral signatures match catalogued emissions from native comets. This similarity might indicate that planet formation follows sufficiently universal processes that cometary composition remains largely independent of stellar specifics. Or it might simply reflect that 3I/Atlas formed around a star similar to our Sun under similar conditions, producing similar outcomes through similar physics. Nitrogen-bearing species receive particular scrutiny. Molecular nitrogen N2 proves extremely difficult to detect directly. It has no permanent dipole moment and thus no strong spectral features in accessible wavelengths. But nitrogen-bearing radicals like CN and NH can be measured, and their abundances relative to carbon and oxygen place constraints on the nitrogen budget. Nitrogen chemistry in protoplanetary disks remains poorly understood. Theoretical models struggle to explain observed nitrogen depletion in comets compared to solar abundances. Whether 3/Atlas shows similar depletion or different nitrogen chemistry could illuminate formation processes or suggest chemical evolution during interstellar travel. Isotopic ratios offer another layer of information encoded in spectral lines. Deuterium heavy hydrogen with a neutron added to the proton appears in trace amounts in water molecules, creating HDO instead of H2O. The DH ratio in cometary water varies among solar system comets, with values typically several times higher than in Earth's oceans, suggesting comets formed from material processed at very low temperatures where deuterium enrichment occurs efficiently. Measuring the DH ratio in 3I/Atlas requires high-resolution spectroscopy capable of distinguishing the small wavelength shifts between HDO and H2O emission features. But such measurements potentially reveal whether deuterium enrichment proceeds similarly around other stars. The spectra accumulate night after night as 3I/Atlas traverses the inner solar system. Different telescopes contribute different wavelength coverage, optical instruments capturing visible emission bands, infrared facilities measuring thermal emission and vibrational transitions, ultraviolet observatories from space detecting OH and atomic hydrogen. The composite dataset grows richer with each observation, each spectrum adding detail, constraining abundances, testing models, and yet ambiguity persists, spectral features overlap, emission from different molecules blends together. Background contamination from Earth's atmosphere complicates ground-based measurements. Extracting robust abundance ratios requires careful analysis, sophisticated radiative transfer modeling, cross-validation between independent measurements. Dust in the coma also reveals itself through spectroscopy. Reflected sunlight from dust grains shows broad features corresponding to silicate minerals. Olivine produces a distinctive emission feature near 10 micrometers in infrared wavelengths, while pyroxene shows different spectral shapes. The exact positions and widths of these silicate features indicate grain composition, crystallinity, and size distribution. Crystalline silicates show sharper features than amorphous silicates. Larger grains produce different spectral slopes than smaller grains. By modeling the observed dust spectrum, researchers infer mineralogy without collecting physical samples. Organic compounds remain the most challenging to characterize. Complex carbon molecules may exist in the dust grains as tarry residues or as discrete particles of polymerized organics, but their spectral signatures often appear as broad, featureless absorption rather than sharp emission lines, making identification difficult without detailed laboratory comparisons. Whether 3I/Atlas contains amino acids, polycyclic aromatics, or other prebiotically relevant molecules remains uncertain. Only direct sample return impossible for an object departing the solar system at hyperbolic velocity could definitively answer such questions. The spectra continue accumulating, photon by photon, building a chemical portrait of material formed around another star. The dust escapes. Grain by grain, particle by particle, the solid component of 3I/Atlas's nucleus lifts away from the surface, carried outward by expanding gases until radiation pressure and orbital mechanics take over, dictating trajectories that will carry some particles across millions of kilometers of space. These grains represent the most ancient solid material in the comet fragments that condensed directly from the gas phase in a protoplanetary disk orbiting an unknown star, that survived incorporation into the growing nucleus, that endured millions of years of cosmic ray bombardment during interstellar travel, that now escape their icy prison to drift independently through our solar system. The size distribution spans enormous range. The smallest grains measure only nanometers across clusters of perhaps a few hundred atoms, barely qualifying as distinct particles rather than large molecules. These nanoparticles formed through condensation in the hottest regions of the origin disk, where temperatures permitted refractory materials to exist as vapor but remained cool enough for nucleation into solid form. Iron atoms, magnesium, silicon, oxygen. These elements combined into tiny crystalline seeds that grew slowly through atomic addition, eventually reaching sizes where gravitational settling could transport them outward into the colder zones. Larger grains, micrometers to millimeters in diameter, likely formed through coagulation, the gentle collision and sticking of smaller particles. In the protoplanetary disk's outer regions, where turbulence remained relatively mild and relative velocities low, dust grains collided frequently enough to build up into larger aggregates. Van der Waals forces held them together initially, later supplemented by ice condensation cementing grains into consolidated structures. The largest dust particles released from 3/Atlas may be fluffy aggregates, internally porous structures containing void spaces between component grains, their effective densities much lower than solid rock. Each grain carries a history written in its mineral structure. Olivine grains show crystalline patterns indicating formation temperatures around 1400 Kelvin, requiring proximity to the young star during the disk's earliest phases. Amorphous silicate particles formed at lower temperatures where crystallization proceeded too slowly to establish ordered structures. Pyroxene, another common silicate, crystallizes at slightly different temperatures than olivine, creating compositional zoning that records cooling rates and thermal gradients. Metallic iron grains, if present, condensed at even higher temperatures, representing material from the disk's innermost regions that somehow migrated outward before becoming incorporated into the comet. What remains mysterious is how these high-temperature grains reach the cold outer disk where comets form. Multiple transport mechanisms operate in protoplanetary disks. Turbulent eddies can loft small particles above the disk mid-plane, carry them radially through the disk, redistribute them across large distances. Stellar winds and radiation pressure push small grains outward. Large-scale disk evolution, viscous spreading, gravitational instabilities, spiral density waves causes material to migrate both inward and outward over the disk's multi-million-year lifetime. The presence of crystalline silicates in 3/Atlas would indicate that such mixing occurred in its origin system, that high-temperature and low-temperature materials became thoroughly blended before cometary assembly. Once released from the nucleus, the grains follow trajectories determined by competing forces. Solar gravity pulls them toward the Sun, following Kepler's laws modified by their initial velocities relative to the comet. But radiation pressure, the momentum transfer from absorbed and scattered photons, pushes small grains away from the Sun, with accelerations that can exceed solar gravity for particles smaller than a few micrometers. The ratio between radiation pressure force and gravitational force, called beta, depends on grain size, composition, and shape. For small grains, beta exceeds unity, meaning radiation pressure dominates and the particles accelerate anti-sunward, contributing to the dust tail's bright appearance. Larger grains, with beta less than unity, experience weaker radiation pressure relative to gravity. They follow trajectories more closely tied to the comet's original orbit, spreading out along the orbital path like breadcrumbs marking where the comet has been. Over weeks and months, these larger particles disperse into an elongated cloud trailing behind the nucleus. Their positions encoding release-timing particles released earlier lie farther along the orbital path than those released more recently. Only took a few million kilometers of travel for the comet to begin shedding its substance across interplanetary space. The dust tails become visible from Earth as scattered sunlight reflects off the grain population. The brightness of the tail depends on the total cross-sectional area of dust particles. More grains or larger grains produce brighter tails and on the scattering efficiency, which varies with grain size and composition. Modeling tail brightness and morphology allows researchers to estimate the total mass of dust released, typically comparable to or exceeding the mass of sublimated gas. Comets lose dust and gas in roughly equal proportions, slowly dismantling their nuclei passage by passage. The escaped dust grains face varied fates. Some will spiral into the Sun over timescales ranging from years to millennia, depending on their orbits and the Poynting-Robertson effect, the gradual orbital decay caused by asymmetric absorption and re-emission of sunlight. Others will be ejected from the solar system entirely, accelerated by radiation pressure or planetary encounters until they achieve escape velocity. A fraction may eventually be captured by planets, entering atmospheres as meteors, burning up in brilliant streaks as atmospheric friction vaporizes them. The tiniest fraction might survive atmospheric entry as micrometeorites, settling to planetary surfaces as extraterrestrial dust, chemically distinguishable from native material through isotopic anomalies. What remains uncertain is whether any dust from 3I/Atlas will ever reach Earth. The comet's trajectory carries it through the inner solar system at a significant angle to Earth's orbital plane, and the dust it releases will inherit orbital properties reflecting that geometry. Most grains will drift into regions of space Earth never crosses, becoming permanent residents of interplanetary space or departing the solar system along paths determined by radiation pressure and gravitational perturbations. The probability of Earth encountering 3I/Atlas's dust trail approaches 0. No meteor shower from this visitor. No physical samples delivered naturally to our planet's surface. Some grains may survive long enough to be collected by future missions. Spacecraft designed to sample interstellar or interplanetary dust could potentially capture particles from 3I/Atlas's dispersing cloud, preserving them in aerogel collectors or impact foils, returning them to Earth for laboratory analysis. Such samples would provide direct access to solid material from another stellar system, a physical connection across light years, a tangible fragment of a world humanity will never visit. The chemistry encoded in those grains, the isotopic signatures, the mineral structures, all would illuminate planet formation processes beyond our solar system. But for now, the grains simply drift, reflecting sunlight, following Newtonian trajectories, carrying their ancient cargo through the widening emptiness. The shape of the trajectory defines destiny. In orbital mechanics, the type of conic section a body traces circle, ellipse, parabola, or hyperbola determines whether that body remains gravitationally bound to its primary or escapes into space. For 3I/Atlas, the mathematics permit no ambiguity. The orbital eccentricity exceeds unity by a comfortable margin, placing the trajectory firmly in hyperbolic territory, ensuring that after this single passage through the inner solar system, the comet will depart forever, climbing back out through the planetary orbits until solar gravity becomes negligible and interstellar space reclaims what it briefly relinquished. The geometry of a hyperbola differs fundamentally from an ellipse. Both are conic sections curves formed by slicing a cone at different angles, but while an ellipse closes on itself forming a loop, a hyperbola opens infinitely, its two branches extending outward without limit. For 3I/Atlas, only one branch matters, the path that brought it in from interstellar space, curved around the Sun at perihelion, and now carries it back outward in a new direction. The Sun sits at one focus of this hyperbolic curve, its gravity bending but not capturing the comet's trajectory, redirecting the path without fundamentally altering the comet's status as a visitor rather than permanent resident. The asymptotes of the hyperbola, those imaginary lines the trajectory approaches at infinite distance, reveal the change in direction. The incoming asymptote points back toward the region of sky from which 3I/Atlas arrived, while the outgoing asymptote indicates the direction it will follow when solar gravity becomes negligible. The angle between these asymptotes, called the deflection angle, depends on perihelion distance and hyperbolic excess velocity. For 3I/Atlas, with its particular orbital parameters, the deflection amounts to roughly 60 degrees significant redirection, but nowhere near the U-turn that would be required to send the comet back where it came from. Perihelion itself, the point of closest approach to the Sun, occurred at approximately 1.4 astronomical units, placing the comet between Earth's orbit and Mars's orbit at its nearest point. This distance represents a compromise between competing interests. Closer approaches would provide more intense solar heating, stronger outgassing, brighter appearances that simplify observation. But closer approaches also accelerate the comet through perihelion more rapidly, reducing the time window when observations are optimal. At 1.4 astronomical units, 3I/Atlas remains observable for weeks around perihelion while experiencing sufficient heating to produce measurable activity. The velocity at perihelion reaches approximately 45 kilometers per second relative to the Sun, typical for hyperbolic comets but impressively fast by terrestrial standards. At this speed, the comet crosses Earth's orbital diameter in less than 3 days. Only took one brief swing around the Sun to transform approach direction into departure direction, to sample the inner solar system's warmth and then leave it behind. The kinetic energy at this velocity overwhelms the Sun's gravitational binding energy by a wide margin, ensuring escape regardless of any reasonable perturbations from planetary encounters. What remains uncertain is whether 3I/Atlas will encounter any planets during its outward journey. The trajectory's inclination and orientation make close approaches unlikely, but statistical possibilities exist. If the comet passes within a few planetary radii of Jupiter or Saturn during outbound flight, gravitational deflection could measurably alter the departure trajectory, changing the outgoing asymptote's direction by degrees. Such an encounter would redirect wherein the galaxy 3I/Atlas eventually travels, potentially affecting whether it ever encounters another stellar system and which star that might be. The trajectory also determines observational opportunities. As 3I/Atlas climbs away from the Sun, it fades steadily both because distance increases and because outgassing diminishes as solar heating weakens. Beyond approximately 3 astronomical units, most comets become difficult to observe as coma production drops and the nucleus shrinks back into dormancy. For 3I/Atlas, the observational window likely extends only a few months past perihelion before the comet becomes too faint for all but the largest telescopes. After that, it continues onward unobserved, its exact position calculable from the refined orbital elements, but its physical state unknown. The hyperbolic trajectory means 3I/Atlas experiences our solar system as a temporary perturbation in an otherwise straight-line journey through the galaxy. In the comet's reference frame, it has been travelling through space for millions of years at approximately constant velocity 15 kilometers per second, relative to the local standard of rest. The Sun's gravity well represents a brief interruption in this journey, a few months or years when the comet's path curves noticeably before resuming nearly straight-line motion. The total change in velocity, the difference between the incoming velocity vector and the outgoing velocity vector, amounts to only a few kilometers per second, a small correction to a journey spanning light years. The orbital energy remains positive throughout the passage, another mathematical signature of unbound trajectories. Objects in elliptical orbits around the Sun possess negative total energy, indicating they're trapped in the potential well. But hyperbolic objects carry positive energy, the sum of kinetic energy and gravitational potential energy always exceeding zero, confirming that no energy barrier prevents escape. For 3I/Atlas, this positive energy derives from whatever ejection event sent it into interstellar space millions of years ago, when a gravitational encounter with a giant planet boosted its velocity beyond the escape speed of its origin system. The geometry also determines the comet's eventual fate. After departing our solar system, 3I/Atlas will continue through the Milky Way on a path slightly different from its approach trajectory. The galactic environment it encounters will remain largely unchanged, the same thin interstellar medium, the same cosmic ray flux, the same distant stars providing negligible illumination. Over millions of years, the comet will drift through interstellar space again, frozen and dark, its brief period of activity forgotten, its surface once more equilibrating with the cosmic microwave background. Eventually, perhaps, it will encounter another star. The statistics suggest that with enough time, tens or hundreds of millions of years, 3I/Atlas will pass within a few light years of some stellar system, close enough for that star's gravity to perturb the trajectory, possibly close enough for capture into a bound orbit if the geometry proves favourable. But most likely it will simply pass through, receive another gravitational deflection, depart again into darkness. Only took one unlucky ejection to condemn the comet to eternal wandering, with only rare and brief interruptions when stellar encounters temporarily illuminate its existence. The hyperbola stretches ahead, patient and inevitable, a geometric destiny that no force within the solar system can alter. The chemistry of planet formation operates according to principles that appear universal. Gravity collapses molecular clouds into spinning disks. Temperature gradients sort materials by condensation temperature. Grains collide and stick. Planetesimals accumulate. Giant planets form and scatter smaller bodies. The physics governing these processes, gravity, thermodynamics, electromagnetism remains constant regardless of stellar mass, metallicity or galactic location, and yet, local conditions vary enough to produce diversity within the underlying similarity. Each planetary system represents one realization of a stochastic process, one roll of cosmic dice constrained by physical law but not determined by it. 3I/Atlas emerged from such a process, its composition encoding specific details about the protoplanetary disk where it formed. The ratios between different ices, the isotopic signatures, the mixture of crystalline and amorphous silicates, all these features depend on local disk conditions. Temperature at the comet's formation distance determined which volatiles condensed and which remained gaseous. The disk's chemical composition, inherited from the parent molecular cloud and enriched by previous stellar generations, set the abundances of heavy elements available for incorporation. The timescale of formation influenced whether slow processes like radial mixing and grain annealing could proceed to completion, or whether rapid comet assembly froze material in non-equilibrium states. Comparisons with solar system comets offer the clearest window into these formation processes. Our comets formed in a disk whose properties are relatively well constrained through meteoritic evidence, planetary compositions, and theoretical modelling. If 3I/Atlas shows composition indistinguishable from solar system comets, the implication is that its origin disk resembled ours in the relevant parameters: similar thermal structure, similar chemical abundances, similar dynamical evolution. Such convergence would suggest that planet formation around Sun-like stars produces similar outcomes, regardless of minor variations in initial conditions. Alternatively, measurable differences in composition would indicate that 3I/Atlas's origin environment differed in some significant way. Perhaps the parent star's mass diverged from solar, creating different luminosity and thus different temperature gradients in the disk. Perhaps the metallicity, the fraction of elements heavier than helium, exceeded or fell short of solar values, affecting the abundances of rock-forming and ice-forming elements. Perhaps the disk's lifetime differed, truncated by nearby massive stars whose radiation dispersed the gas prematurely, or extended by isolation in a quiet molecular cloud, allowing slow chemical processes to reach completion. What remains mysterious is whether the observed similarities between 3I/Atlas and solar system comets reflect genuine similarity in formation or merely selection effects. Interstellar comets detected from Earth are necessarily those bright enough to observe, which correlates with size and activity level, which depends on volatile content. Comets with unusual compositions that sublimate weakly or produce little dust might pass through undetected. The small sample size, only 3 confirmed interstellar objects, precludes robust statistical statements about the underlying population. Every interstellar comet discovered might represent an outlier, an unusual member of its origin system that happened to be ejected. While typical comets from other stellar systems remain invisible in our surveys, the nitrogen budget presents a particular puzzle. Solar system comets show nitrogen depletion relative to solar abundances, with molecular nitrogen N2 especially scarce. Various explanations have been proposed in efficient incorporation of nitrogen into ices, conversion to ammonia through surface chemistry, loss during thermal processing events, but consensus remains elusive. If 3I/Atlas shows similar nitrogen depletion, the implication is that whatever process removes nitrogen operates universally. If nitrogen abundances differ, formation environment or subsequent processing must vary between stellar systems in ways affecting nitrogen chemistry specifically. Deuterium enrichment offers another comparative diagnostic. Water in solar system comets typically shows DH ratios 2 to 3 times higher than in Earth's oceans, indicating formation at very low temperatures where deuterium partitions preferentially into ice over gas. The exact DH ratio varies among different cometary families. Jupiter family comets originating in the Kuiper belt show different enrichment than Oort cloud comets, presumably formed closer to the giant planets before being scattered outward. These variations reflect formation location and thermal history. Measuring 3I/Atlas's DH ratio places it within this taxonomy, identifying whether its formation environment resembled the inner regions where giant planets scattered material or the outer regions where material accumulated undisturbed. The silicate mineralogy carries information about thermal processing in the disk. Crystalline silicates require temperatures above approximately 1000 Kelvin to form, either through direct condensation from hot gas or through annealing of amorphous precursors. Their presence in comets indicates that high-temperature material became transported to cold outer regions where comets assembled. The crystalline to amorphous ratio varies among solar system comets, suggesting different mixing efficiencies or different disk structures. If 3I/Atlas shows high crystalline fractions, its origin disk must have efficiently transported inner disk material outward. Low crystalline fractions would indicate isolation between hot and cold zones, limited radial mixing, or formation in a disk that remained too cool for crystallization. Only took a few spectrum measurements to pose these questions, but answering them requires observations that push current instrumental capabilities. Isotopic ratios demand high spectral resolution to separate closely spaced lines. Weak molecular bands require large collecting areas and long integration times. Dust mineralogy needs infrared spectroscopy covering wavelength ranges where atmospheric absorption complicates ground-based observations. Each measurement carries uncertainties. Each derived ratio spans a range of possible values. Each comparison with solar system comets must account for the diversity within the reference population. And yet, patterns emerge from comparative studies. The compositions of solar system comets, despite variation, cluster within relatively narrow ranges for most volatile ratios. This clustering suggests that planet formation processes produce outcomes that, while not identical, remain constrained by the physics of protoplanetary disks. If 3I/Atlas falls within these clusters, the interpretation is that disk chemistry operates similarly around different stars. If it lies outside, boundary conditions must differ: stellar mass, metallicity, disk lifetime, external radiation field, some parameter that shifts the chemical equilibria or kinetic pathways in measurable ways. The organic component remains largely uncharacterized. Complex carbon molecules likely exist in the dust and in the ices, but spectroscopic signatures remain ambiguous. Broad features difficult to interpret without laboratory analogues for comparison. Whether 3I/Atlas contains amino acids, whether their chirality shows preferences, whether polycyclic aromatics appear in similar abundances to solar system comets, These questions await better data or sample return missions that remain technological fantasies for interstellar objects. The composition of 3/Atlas thus serves dual purposes. It illuminates the specific disk where this particular comet formed, constraining conditions billions of years ago and light years distant. And it contributes one more data point to the comparative study of planet formation, helping to distinguish universal processes from variable outcomes, identifying which aspects of disk chemistry depend sensitively on local conditions and which remain robust against parameter variations. Each interstellar comet discovered adds to this dataset, gradually building an empirical understanding of how planetary systems form across the galaxy. The measurements continue, photon by photon, refining abundances, narrowing uncertainties, testing models against observation. From the perspective of 3/Atlas, Earth appears unremarkable, just another rocky planet orbiting at a typical distance from a typical star, indistinguishable from countless similar worlds throughout the galaxy except by precise measurement of orbital parameters and atmospheric composition. As the comet swings through the inner solar system, Earth crosses its field of view if the comet possessed eyes. If it could observe rather than simply exist as a pale blue point barely brighter than the background stars, a speck occasionally transiting across the sun's disk from the comet's vantage point, revealing its presence through positional shifts measured in fractions of a degree. The geometry places Earth several astronomical units from 3/Atlas during closest approach, too distant for the planet's features to resolve as anything more than a point source. No continents visible, no oceans, no atmospheric banding, no cloud patterns, just integrated light from a sphere roughly 12,000 kilometers in diameter, reflecting approximately 30% of incident sunlight. The blue color, so distinctive in close-up images, blurs into white when observed from such distances, the specific wavelength distribution of reflected light providing the only clue to atmospheric composition. Oxygen absorption bands in the spectrum, water vapor features, the subtle signatures of biological activity affecting atmospheric chemistry, all these remain detectable in principle but require instruments far more sophisticated than passive observation. The comet itself carries no instruments, it measures nothing, records nothing, processes no information beyond the thermodynamic responses to solar heating. The anthropomorphic notion that 3/Atlas might be collecting information about Earth or other planets represents projection of human concerns onto indifferent physics. Comets do not observe. They respond mechanically to forces gravity, radiation pressure, thermal gradients following deterministic paths through phase space without awareness, intention, or memory. Only took a few billion years of human cognitive evolution to produce entities capable of wondering whether unconscious objects might wonder about them. But in a physical sense, the comet does carry information acquired during its passage. Solar wind particles, protons and electrons streaming outward from the sun at hundreds of kilometers per second impact the coma, some becoming ionized and swept away by magnetic fields, others embedding themselves in dust grains or even reaching the nuclear surface. These particles carry isotopic signatures characteristic of our Sun, ratios of deuterium to hydrogen and helium, 3 to helium-4 that distinguish solar material from interstellar medium. Over the weeks or months of active outgassing, countless solar wind particles collide with gas molecules in the coma, a tiny fraction becoming incorporated into the physical structure of escaping dust grains. Photons from the sun impart their own signature. Ultraviolet radiation energetic enough to break chemical bonds processes the surface material, creating new molecular species that did not exist before solar exposure. Radicals form and recombine. Organic molecules polymerize. Ice structure changes as energy absorption triggers phase transitions. The surface chemistry of 3/Atlas after perihelion differs measurably from its state before perihelion, modified by solar radiation in ways that encode information about exposure duration, intensity, and wavelength distribution. The nucleus will carry this processed rind back into interstellar space, a thin layer altered by our Sun's influence. What remains uncertain is whether any of this acquired material will survive the journey. Cosmic ray bombardment during millions of years of subsequent interstellar travel will continue processing surface layers, destroying solar wind implantations, erasing radiation-induced chemistry, gradually removing any record of the solar encounter through cumulative damage. The timescale for complete erasure depends on nucleus size, on material properties, on the specifics of cosmic ray interactions with ice and dust. But over 10 million years, over 100 million years, the probability approaches unity that all solar signatures will be obliterated, leaving no detectable trace that 3I/Atlas ever passed through our system. Gravitational influences provide more persistent information transfer. The Sun's gravity well deflected 3I/Atlas's trajectory by approximately 60 degrees, permanently altering the comet's path through the galaxy. This deflection encodes information about solar mass. A different stellar mass would produce different deflection angles for the same incoming velocity and perihelion distance. An observer in another stellar system, encountering 3I/Atlas millions of years hence and measuring its trajectory precisely enough to trace it backward, could in principle constrain the mass of the star it previously encountered. Gravitational deflection serves as information transfer across cosmic distances and timescales. Though extracting that information requires precision measurements unlikely to occur, the planet's gravitational fields also perturb the trajectory minutely. Jupiter, despite lying far from 3I/Atlas's path, exerts measurable force across astronomical unit distances. The cumulative deflection amounts to perhaps a few arcseconds, negligible compared to solar deflection but theoretically detectable with sufficiently precise astrometry. This tiny perturbation carries information about Jupiter's mass and position, encoded in the modified trajectory as a permanent record that future observers might decode. Only took one passage through a planetary system to acquire gravitational imprints from multiple bodies, subtle deflections that persist indefinitely. From Earth's perspective, 3I/Atlas appears as one more astronomical object among millions, distinguished primarily by its unusual trajectory and interstellar origin. Telescopes track its position, spectrometers analyze its composition, cameras capture images of its coma and tails. The comet becomes data numerical measurements stored in databases, spectral features plotted on graphs, orbital elements refined to increasing precision. This transformation of physical object into information represents humanity's primary mode of knowing distant things, reduce them to measurements, compress complexity into manageable data sets, extract patterns that permit comparison and understanding. But the reverse information flow, what 3I/Atlas learns about Earth or humanity, remains negligible. Photons reflected from Earth reach the comet, carrying information encoded in their wavelengths and intensities. Radio transmissions leak into space, electromagnetic signatures of technological civilization propagating outward at light speed. Some tiny fraction of these photons and radio waves intercept 3I/Atlas's trajectory, strike its nucleus or coma, transfer infinitesimal amounts of energy and momentum. In principle, these interactions encode information about Earth's existence, but without receivers to detect them, without instruments to decode them, without minds to interpret them, the information remains latent, unactualized, meaningless. The relationship thus remains asymmetric. Humanity observes 3I/Atlas intensively, extracting information, building models, publishing papers. The comet, indifferent and unconscious, continues along its trajectory, physically affected by solar system interactions in ways that encode information without recording it, carrying markers of this passage that will likely be erased long before they could be read by any hypothetical future observer. Information flows primarily in one direction from comet to humanity, from distant object to curious minds, from cosmos to comprehension. The pale blue dot fades in the comet's wake, Earth receding to stellar insignificance as 3I/Atlas climbs outward, its brief proximity to our world already becoming history. The only data 3I/Atlas truly collects consists of physical imprints that require no awareness to acquire. Solar wind particles embed themselves in the nuclear surface through direct collision, their arrival times and energies recorded in the spatial distribution and depth profile of implanted atoms. Photons absorbed by ice molecules break bonds and trigger photochemistry. The products of these reactions encoding wavelength and intensity of incident radiation through the specific molecular structures. Gravitational interactions bend the trajectory, each planet's mass and position inscribed permanently in the modified orbital elements. This is information in the physicist's sense, correlations between different states of matter that allow past events to be inferred from present configurations, but not information in any cognitive sense, requiring observation or storage or retrieval. The solar wind flux at 3I/Atlas's perihelion distance averages roughly 5 protons per cubic centimeter, moving at 400 kilometers per second. These particles stream outward from the Sun's corona, accelerated through mechanisms still incompletely understood, involving magnetic reconnection and wave-particle interactions. When they encounter the comet's expanding coma, complex interactions occur. Some solar wind protons charge exchange with neutral molecules in the coma, stealing electrons and becoming neutral hydrogen while ionizing cometary molecules. Other protons collide with dust grains, transferring momentum, occasionally sticking to grain surfaces or embedding themselves within surface layers. The flux integrated over the weeks near perihelion delivers approximately 10 circumflex 16 solar wind protons per square meter to surfaces oriented toward the Sun. Most of these particles interact with gas and dust in the coma, never reaching the nucleus. But some fraction penetrates through the tenuous inner coma to strike the nucleus surface directly. There they thermalize, losing kinetic energy through collisions with surface molecules, coming to rest at shallow depths typically measured in nanometers to micrometers. The implanted hydrogen atoms, with their solar isotopic signature, become trapped within the ice matrix, distinguishable in principle from native hydrogen by their slightly different deuterium to hydrogen ratio. What remains uncertain is the retention efficiency. Implanted atoms in ice may not remain stable. Diffusion permits migration through the crystal lattice, especially if solar heating raises surface temperatures enough to increase atomic mobility. Sputtering by subsequent cosmic ray impacts can eject implanted atoms back into space. The photochemistry driven by ongoing solar ultraviolet exposure may incorporate implanted hydrogen into new molecular species that then sublimate, carrying the solar signature away in the coma. Over the millions of years between this solar passage and any hypothetical future encounter with another star, the probability that solar wind implantations survive in detectable quantities approaches zero. Photon interactions provide another form of information transfer. Every ultraviolet photon absorbed by the nuclear surface deposits energy into molecular bonds, often breaking these bonds and creating reactive fragments. Water ice exposed to UV radiation photodissociates into hydrogen and oxygen, with subsequent chemistry producing hydrogen peroxide, ozone, and other species not present in the original ice. Organic molecules polymerize under UV exposure. Simple species like methane and carbon monoxide linking together to form increasingly complex chains and rings. This radiation chemistry proceeds according to well-studied mechanisms, each photon's wavelength determining which bonds break and which reactions become energetically accessible. The integrated UV dose near perihelion modifies the surface composition measurably. Models suggest that the top millimeter or so of the nucleus experiences significant chemical alteration, with perhaps 10 to 20% of molecules undergoing radiation-induced reactions. Deeper material remains shielded by overlying layers, preserved in its original state. The result is a chemically stratified surface, a processed rind overlying pristine interior that encodes information about UV exposure, duration, and intensity. Only took a few weeks of sunlight to rewrite surface chemistry accumulated over millions of years of interstellar dormancy. But again, permanence remains questionable. Once 3I/Atlas departs the solar system and recools to equilibrium with the cosmic microwave background, cosmic ray bombardment becomes the dominant radiation source. Cosmic rays carry far more energy per particle than solar UV photons, penetrating deeper and causing more extensive chemical disruption. Over millions of years, cosmic ray processing will erase the solar UV signature, replacing it with a different chemical profile characteristic of interstellar radiation exposure. The memory of this solar passage, written in molecular structures, eventually degrades beyond recognition. Gravitational deflection provides the most permanent information transfer, unlike surface implantations and photochemistry, which can be erased by subsequent radiation processing. The change in trajectory persists indefinitely unless another gravitational encounter occurs. The 60-degree deflection angle, combined with the specific change in velocity magnitude, uniquely identifies the passage through a stellar system with particular mass and geometry. This information remains encoded in the orbital elements in the direction of the velocity vector, in the specific value of hyperbolic excess velocity, for as long as the comet maintains its integrity as a coherent object. Future observers, if any exist, could in principle decode this information. By measuring 3I/Atlas's position and velocity with sufficient precision and tracing the trajectory backward through time, they could identify regions of space where the comet must have experienced significant gravitational influence. Combining this geometric constraint with knowledge of stellar motions and positions throughout the galaxy, they might narrow down candidate stars responsible for the deflection. Further constraints from spectroscopic measurements detecting solar origin isotopes if they survive. Analyzing chemical signatures characteristic of our Sun's output could potentially identify our solar system as the source of the deflection. But the probability of such detailed forensic analysis approaches zero. The galaxy contains hundreds of billions of stars. Stellar motions erase positional information over tens of millions of years as stars drift through the spiral arms, their galactic orbits carrying them to different locations. Isotopic signatures, if they survive at all, require sample return missions to detect with sufficient precision. The information is present in principle but practically inaccessible, encoded in physical states that no future observer will likely measure with sufficient precision to extract meaningful conclusions. What 3I/Atlas carries forward most faithfully is simply its own composition, the ices and dust and organic molecules assembled in its origin disk, preserved through interstellar travel despite cosmic ray processing, briefly exposed and partially altered during solar passage, now returning to frozen dormancy for the next stage of its journey. This compositional information, intrinsic to the comet rather than acquired during passage, represents the primary scientific value. The solar system's contribution implanted atoms, UV-processed molecules. Gravitational deflections adds minor footnotes to a story written billions of years ago in a protoplanetary disk light years away. The information flows in all directions but persists unevenly. Some transfers written in permanent gravitational deflections, others scrawled in ice that cosmic rays will erase given time. The detection of 3I/Atlas represents statistical fortune more than targeted discovery. Automated sky surveys designed to catalogue asteroids and search for near-Earth objects happen to capture interstellar visitors as incidental byproducts, their unusual trajectories flagging them as objects requiring additional scrutiny. But the surveys remain incomplete, their coverage patchy, their sensitivity limited by telescope aperture and detector capabilities. Most interstellar objects pass through undetected, too faint or too distant, or simply in the wrong patch of sky when observations occur. The few discoveries achieved so far suggest a much larger population moving through the solar system continuously. Invisible to current instruments. Statistical modelling based on the 3 confirmed interstellar objects yields estimates of the population size and flux rate. Extrapolating from detection rates and accounting for observational biases, surveys preferentially detect larger objects on trajectories that bring them close to Earth. Researchers calculate that perhaps 1 to 2 interstellar objects larger than 100 meters cross the inner solar system annually. Smaller objects arrive more frequently, following the typical size-frequency distribution where numerous small bodies exist for every large one. If this scaling continues down to meter-sized objects, hundreds might pass through annually at sizes below a meter, thousands or tens of thousands. The vast majority remain undetectable with existing telescopes. An object a few meters across, moving at hyperbolic velocity through the outer solar system, reflects so little sunlight that even sensitive wide-field surveys would miss it unless it happened to pass extremely close to Earth. Only the largest interstellar visitors, those hundreds of meters across or larger, or those that approach the Sun closely enough to develop bright comet through outgassing, stand reasonable chances of discovery. The 3 confirmed detections likely represent the brightest tail of a distribution extending orders of magnitude fainter. What remains uncertain is whether the estimated flux rates accurately represent the true population. With only 3 confirmed objects, statistical uncertainties remain large. Perhaps the actual flux is half the estimated value, or double, or varies by factors of 10 depending on assumptions about size distribution and activity levels. Perhaps interstellar object populations vary with galactic location, stellar density, star formation history, and dynamical environment might affect ejection rates and the resulting density of wandering comets and asteroids. The solar system orbits within the galactic disk where stellar encounters remain relatively infrequent, but other regions might show higher interstellar object densities. The size distribution particularly affects population estimates. If interstellar objects follow the same power law size distribution as solar system comets and asteroids, with each factor of 10 decrease in size corresponding to roughly a 100-fold increase in number, then small interstellar bodies should vastly outnumber large ones. But this scaling may not hold. Ejection mechanisms might preferentially remove certain size ranges. Collisional grinding in the interstellar medium could deplete small objects over time. Observational biases remain so severe that confirming or refuting the assumed size distribution requires many more detections spanning a wider range of sizes. The origin populations also remain poorly constrained. Interstellar objects could come from planetary systems at various evolutionary stages. Newly forming systems with massive protoplanetary disks might actively eject material through gravitational scattering as giant planets migrate and interact. Mature systems might still occasionally scatter objects to escape velocity through planetary encounters or stellar flybys. Old systems where planets have settled into stable configurations might contribute less to the interstellar population. Binary stellar systems, where 2 stars orbit each other, might produce different ejection rates than single-star systems due to their more complex gravitational environments. Only took 4 billion years of solar system existence for humanity to develop the capability to detect these visitors. But the capability remains crude. Current surveys find only the most obvious objects, those bright and close enough to stand out clearly against the stellar background. Fainter objects, more distant objects, objects with low albedos or inactive surfaces all pass through unnoticed. The known interstellar objects represent selection effects as much as representative samples, picked from the population by observational biases that favor certain characteristics over others. the temporal distribution of discoveries also carries limited information. 3 detections spread across several years might suggest a steady flux rate, or might simply reflect the statistics of rare events. Poisson statistics governing random arrivals permit significant clustering. Several detections in quick succession, followed by long gaps, remain consistent with uniform underlying flux. Without decades of consistent surveying, distinguishing between variable and constant flux rates remains impossible. Perhaps interstellar object density varies with the solar system's position in its galactic orbit, increasing when passing through spiral arms where stellar density rises, decreasing in the quieter regions between arms. The composition distribution across the interstellar population remains almost entirely unknown. If most interstellar objects resemble 3I/Atlas and 2I/Borisov cometary bodies rich in volatiles, then the galaxy's interstellar medium receives continuous enrichment with water ice, organic molecules, and other biologically relevant materials. If instead most interstellar wanderers consist of rocky or metallic asteroids with minimal volatile content, the chemical implications differ. The 2 or 3 confirmed objects provide insufficient sampling to establish compositional demographics, to determine what fraction show cometary activity versus asteroidal appearance, to measure the range of volatile abundances across the population. Future surveys promise increased detection rates. The Vera C. Rubin Observatory, with its large aperture and wide field of view, should discover interstellar objects at rates perhaps 10 to 20 times higher than current surveys once operational. Space-based infrared telescopes could detect interstellar objects through their thermal emission, even when too faint for optical detection. Dedicated networks of small telescopes scanning the entire sky nightly would catch objects current surveys miss. Each improvement in observational capability brings the population into clearer focus, transforming statistical estimates based on a handful of detections into empirical distributions based on hundreds or thousands. But even with improved surveys, most interstellar objects will continue passing through undetected. The combination of faintness, speed, and sky coverage limitations ensures that comprehensive census remains impossible with foreseeable technology. The solar system swims through a river of interstellar traffic that only occasionally becomes visible when circumstances align favorably, when an object passes close enough, when it brightens through outgassing, when a telescope happens to point in the right direction at the right time. The statistics accumulate slowly, detection by detection, refining estimates of how many wanderers cross through our neighborhood, how often collisions might occur, what fraction of Earth's water or organic molecules might trace origins to interstellar delivery. The observatories turn their attention skyward with patient precision, large telescopes on remote mountaintops, their mirrors polished to nanometer smoothness, their pointing systems accurate to fractions of an arcsecond, track 3I/Atlas across the background stars. Each observation adds data points to growing archives' photometric measurements, recording brightness variations that reveal rotation periods and axis orientations, spectroscopic data capturing emission lines from sublimating volatiles, astrometric positions refining the orbital solution to ever higher precision. The comet becomes a distributed object, its physical presence in space mirrored by accumulating data sets stored in servers scattered across continents. Different facilities contribute different capabilities. Wide-field survey telescopes discover the object initially, their automated pipelines flagging unusual motion and triggering alerts that propagate through astronomical networks. Larger research telescopes perform follow-up observations, their greater light-gathering power permitting spectroscopy and detailed photometry. Radio telescopes measure hydroxyl maser emission at 18 centimeter wavelength, a powerful diagnostic of water production rates. Space-based observatories access wavelength ranges blocked by Earth's atmosphere. Ultraviolet emissions from hydrogen and oxygen, infrared bands revealing carbon dioxide and carbon monoxide, X-rays produced when solar wind ions charge exchange with cometary neutrals. The coordination occurs through established channels. The Minor Planet Center collects astrometric observations from observatories worldwide, computing refined orbits and disseminating updated elements. The Comet Observation Database archives photometric measurements, tracking brightness evolution as the comet approaches and recedes from perihelion. Spectroscopic databases store reduced spectra from multiple instruments, permitting comparative analysis and searches for temporal variations in composition. This distributed network of observations and archives transforms a single transient object into a shared scientific resource accessible to researchers globally. What remains challenging is maximizing observational efficiency during the limited time window when 3/Atlas remains bright enough for detailed study. Telescope time allocates competitively. Many projects compete for access to premier facilities. And even high-priority targets like interstellar objects must share time with other scientifically valuable observations. Observing proposals must justify requested hours, specify required instrument configurations, demonstrate feasibility within technical constraints. Successful proposals receive allocations measured in hours or nights, carefully scheduled to optimize signal-to-noise given the comet's predicted brightness and observing conditions. Weather introduces additional uncertainty. Clear skies remain essential for ground-based optical and infrared observations, but weather forecasts provide only probabilistic guidance days in advance. Scheduled observing nights sometimes yield no data when clouds obscure the sky. Backup targets permit productive use of telescope time when primary targets become unobservable, but time lost to weather cannot be recovered for objects fading as they recede from the sun. Only took millions of years for the comet to cross interstellar space and arrive at our solar system, but only weeks or months of clear skies to gather data before it fades beyond instrumental reach. The technical demands vary by observation type. Spectroscopy requires higher signal-to-noise than photometry, necessitating longer exposures or larger telescopes. High-resolution spectroscopy capable of measuring isotopic ratios demands the largest apertures and most sophisticated spectrographs, with integration times extending to hours for single spectral ranges. Infrared observations require dry atmospheric conditions to minimize water vapor absorption that contaminates spectral features. Radio observations need clear sightlines to the comet unobstructed by terrain or radio frequency interference from human activities. Coordinated campaigns maximize scientific return by simultaneously observing at multiple wavelengths. When a large optical telescope obtains spectra, radio observations measuring hydroxyl emission provide complementary data on gas production. Infrared measurements of dust. Thermal emission constrain grain properties while optical imaging reveals coma morphology. These simultaneous observations sample the same outgassing state, permitting direct comparison between techniques and reducing uncertainties introduced by temporal variability. Scheduling such campaigns requires coordination across observatories in different time zones, careful timing to ensure overlapping visibility, and flexible planning to accommodate unexpected circumstances. What remains uncertain is whether current observations capture the full range of 3/Atlas's behavior. Comets often show sporadic outbursts, sudden increases in activity driven by subsurface volatile release. Rotational effects exposing fresh icy surfaces to sunlight, or other mechanisms incompletely understood. If such outbursts occur during gaps between scheduled observations, they might go undetected, their signatures fading before the next observing opportunity. Continuous monitoring would catch transient events but remains impractical given finite telescope resources and the need to observe many objects. Amateur astronomers contribute valuable observations despite smaller telescopes and less sophisticated equipment. Their flexibility and distributed geographic locations provide coverage complementing professional facilities. brightness measurements obtained with 30-centimeter telescopes, while less precise than those from 8-meter instruments, still constrain activity levels and rotation periods when accumulated over many nights. CCD images from backyard observatories document coma morphology changes between professional observations. These amateur contributions, aggregated through online platforms and submitted to centralized databases, enhance temporal coverage and increase the probability of detecting unexpected behavior. The observing strategy evolves as the comet's behavior becomes clearer. Initial observations establish basic parameters: orbit, activity level, rotation period, rough composition. Subsequent observations refine these measurements and search for variability. As perihelion approaches, observing cadence increases to capture peak activity. After perihelion, observations gradually decrease in frequency as the comet fades, eventually reaching the point where even the largest telescopes struggle to detect signal above background noise. The final observations might occur months after perihelion, squeezing the last photons from a barely detectable object before it vanishes into the outer solar system. Future facilities promise expanded capabilities. Larger telescopes with adaptive optics systems could potentially resolve the nucleus, separating it spatially from the surrounding coma and permitting direct measurement of its size and rotation. Spectroscopic instruments operating at higher resolving power could measure isotopic ratios currently inaccessible. Space missions, though technologically challenging and financially expensive for interstellar targets, could provide in situ measurements unattainable from Earth-based observations, direct sampling of coma gas, close-up imaging of nucleus topography, measurements of magnetic field interactions, but such missions require years to plan and execute. And 3 I/Atlas moves too quickly for intercept given current propulsion technology. Any spacecraft launched toward the comet's predicted position would arrive long after the comet departed that region of space. Plausible intercept trajectories require knowing the object's orbit months or years before closest approach, permitting mission design and spacecraft construction. For now, remote observation remains the only option. Telescopes the only tools available for extracting information from this visitor. The observations continue as long as photons permit, accumulating data point by data point, spectrum by spectrum, extending human knowledge a few more decimal places toward completeness. The impossibility settles in through orbital mechanics. 3 I/Atlas moves at hyperbolic velocity speeds that dwarf the capabilities of current spacecraft propulsion systems. Intercepting the comet would require matching its velocity vector, a maneuver demanding delta V far exceeding what chemical rockets can provide, even with gravitational assists from multiple planetary flybys. The comet's trajectory, inclined significantly to the ecliptic plane and oriented unfavorably relative to planetary positions, compounds the difficulty. No mission architecture exists within present technology that could reach 3 I/Atlas before it fades beyond the outer solar system. Could rendezvous with sufficient time for meaningful study. Could return samples to Earth for laboratory analysis. The numbers illustrate the challenge starkly. Chemical rockets achieve exhaust velocities around 4 kilometers per second, requiring mass ratios, the ratio of fueled spacecraft to dry spacecraft, that grow exponentially with desired velocity change. Reaching 3 I/Atlas's velocity of 45 kilometers per second at perihelion would demand mass ratios exceeding 10,000 to 1, meaning 99.99% of launch mass would be propellant, leaving negligible mass for spacecraft structure, instruments, and payload. Even nuclear thermal propulsion, with exhaust velocities perhaps double those of chemical systems, cannot close the gap between what physics permits and what engineering achieves within realistic constraints. Gravitational assists provide velocity changes without propellant expenditure, but require specific geometric alignments between planetary positions and desired trajectories. The comet's path through the solar system offers few opportunities for beneficial assists. Jupiter lies too far from the trajectory, Saturn even more so, and the inner planets provide insufficient velocity change to matter. A mission launched after 3Y/Atlas's discovery might manage one planetary flyby before the comet departs to distances where solar power becomes impractical and communication delays prohibitive. Only took one unfavourable orbital geometry to place the comet beyond practical reach, despite its proximity to Earth on cosmic scales. What remains theoretically possible are flyby mission spacecraft that intercept the comet's trajectory without matching its velocity, passing at high relative speed while grabbing brief measurements during the encounter. Such missions face their own challenges. At relative velocities of tens of kilometers per second, the encounter duration measures in hours or minutes, limiting observation time. Communication delays minutes to tens of minutes for signals traveling between spacecraft and Earth at light speed prevent real-time command sequences, requiring autonomous operation and pre-programmed observation plans. Instrument pointing must track a rapidly moving target, maintaining alignment despite spacecraft vibration and trajectory uncertainties. Even flyby missions require years to execute. Spacecraft design, construction, testing, launch vehicle integration. These steps consume time measured in years even for streamlined programs. For 3I/Atlas, discovered only months before perihelion, no mission could be prepared quickly enough to intercept during the optimal observation window. By the time a spacecraft could launch, the comet would have receded to distances where encounter geometry becomes unfavourable, or where the comet's diminishing activity reduces scientific value below the mission's cost threshold. Future interstellar objects might permit better preparation if detected earlier. Surveys improving in sensitivity and sky coverage could discover incoming objects years before perihelion, providing lead time for mission planning. A dedicated spacecraft maintained in ready state, awaiting targets of opportunity, could launch on short notice when interesting objects appear. Such concepts remain speculative. Proposals discussed in conference presentations and planning documents, but not yet funded or implemented. The infrastructure for rapid response interstellar object missions does not exist, and its development requires sustained investment in observational networks, spacecraft technology, and mission operations capabilities. What missions could accomplish, given sufficient warning and resources, remains tantalizing. Sample return from an interstellar object would provide direct laboratory access to material from another stellar system, pristine ices, organic molecules, silicate grains, all available for detailed analysis with instruments far more capable than those deployable on spacecraft. Isotopic ratios could be measured with precision impossible through remote spectroscopy. Complex organic chemistry could be characterized with mass spectrometry and chromatography. Mineral structures could be examined with electron microscopy. A few grams of returned sample would yield more information than months of telescopic observation. Close-up imaging would reveal surface topography at meter or centimeter resolution crater, distributions recording impact history, layering exposing internal structure, active regions showing where sublimation concentrates. These morphological details constrain formation and evolution models, distinguish between competing hypotheses about cometary assembly and processing. Remote observations integrate light over the entire visible disk, averaging away spatial variations that close-up imaging would resolve. Only direct proximity permits the spatial resolution needed to see geology rather than statistics. In situ measurements of the coma would sample gas and dust directly, determining composition without the uncertainties inherent in remote sensing. Mass spectrometers could identify molecular species too faint for spectroscopic detection, measure isotopic ratios in real time, track temporal variations in outgassing composition. Dust analyzers could measure grain size distributions, determine elemental abundances, characterize organic content at molecular levels. These measurements, obtained within the coma rather than from millions of kilometers distance, bypass many of the assumptions and models required to interpret remote observations. But 3I/Atlas will receive no such attention. It passes through observed only from afar, studied only through photons collected by ground-based and space-based telescopes, characterized only to the precision those photons permit. The comet continues along its hyperbolic trajectory, indifferent to human curiosity, following gravitational imperatives that care nothing for scientific value or the limitations of technology. And gradually it fades, first dropping below the sensitivity threshold of small telescopes, then becoming challenging even for larger instruments, eventually requiring the most capable observatories to detect at all. The last observations might occur a year after discovery, perhaps longer if the comet proves unusually bright. Then it passes beyond even the largest telescope's reach, continuing outward through the outer solar system in silence, its position calculable from orbital elements, but its physical state unobservable, its activity level unknown, its fate a matter of extrapolation rather than measurement. Somewhere between Uranus and Neptune, somewhere in the cold darkness where sunlight provides negligible heating and volatiles return to dormancy, 3I/Atlas transitions back to the frozen state it maintained during millions of years of interstellar travel. The opportunity passes, unrepeatable. This particular visitor will never return, will never offer another chance for study, will carry its secrets back into the space between stars where no human instruments can follow. Only the accumulated data remain spectra, images, orbital elements, photometric measurements archived in databases, analyzed in research papers, gradually incorporating into the collective understanding of interstellar objects and planet formation processes. The messages humanity cannot send follow the comet into silence. The fading begins imperceptibly. At first, brightness measurements show only the expected decline following the inverse square law of distance and the decreasing solar heating that reduces outgassing rates. The coma remains visible in large telescopes, its spectral features still measurable despite weakening signal. But as 3I/Atlas crosses beyond Jupiter's orbit, as distance from the Sun stretches past 5 astronomical units and then 6, the production rates of gas and dust fall exponentially. Water sublimation nearly ceases when surface temperatures drop below approximately 180 Kelvin. Only the most volatile ices carbon monoxide, carbon dioxide, molecular nitrogen continue sublimating at the diminished solar flux reaching these outer regions. The coma contracts as gas production wanes. Fewer molecules escape the nucleus each second, reducing the density and extent of the glowing envelope. The dust production drops correspondingly with less gas flow to lift particles from the surface. Fewer grains enter the coma and tails. The visible appearance shifts from a diffuse cloud with extended tails to a more compact haze, barely distinguishable from a stellar point source at typical telescope resolutions. Photometric measurements require longer exposure times to achieve acceptable signal-to-noise, and even then, uncertainties grow as the object approaches the threshold where background sky brightness overwhelms the faint signal from the comet. The spectroscopic observations become especially challenging. Dispersing the already faint light into component wavelengths spreads the available photons across many detector pixels, reducing signal per pixel to levels where noise dominates. Emission features that appeared clearly in spectra, obtained near perihelion, now barely rise above the background fluctuations. Measuring production rates or compositional ratios from these degraded spectra introduces large uncertainties, makes distinguishing between molecular species difficult, eventually becomes impossible as the comet fades further. Only took a few astronomical units of additional distance to transform unambiguous detections into marginal measurements teetering at the edge of instrumental capabilities. What remains uncertain is the exact distance at which 3I/Atlas becomes completely inactive. Different volatiles cease sublimating at different heliocentric distances depending on their vapor pressures and the nucleus's thermal properties. Carbon monoxide, with its lower sublimation temperature, might continue outgassing beyond distances where water has long since frozen dormant. But even carbon monoxide eventually reaches distances where solar heating becomes insufficient, where surface temperatures equilibrate with the cosmic microwave background plus faint sunlight, where sublimation rates drop to negligible levels. The transition from active comet to inert nucleus probably occurs gradually rather than abruptly, activity declining smoothly over a range of distances until outgassing effectively ceases. The nucleus itself, stripped of its obscuring coma, should become observable in principle once gas and dust production stops. But the nucleus's small size and low albedo make it extraordinarily faint. A body a few hundred meters across reflecting only 4 or 5% of incident sunlight at distances beyond 10 astronomical units challenges even large telescopes. The nucleus appears stellar, a point source indistinguishable from background stars except through its motion. Tracking it requires precise astrometry, measuring its position relative to reference stars, calculating updated orbital elements that predict future positions. Any gap in observations risks losing the object entirely, its faintness making recovery difficult if searches must cover large sky areas. The final confirmed observations might detect the nucleus only marginally, signal buried in noise, position measurements carrying uncertainties of arcseconds rather than the milli-arcsecond precision achieved near perihelion. These last data points contribute to refining the orbit, but with diminishing impact the trajectory is already well determined from earlier high-quality measurements, and additional observations at large distances add little new information. The scientific value of continued tracking decreases as the comet fades, eventually falling below the threshold where telescope time becomes better spent on other objects offering clearer signals and richer data. Then 3I/Atlas passes beyond reliable detection, continuing outward along a trajectory that remains calculable but unobserved. The comet crosses Neptune's orbit, ventures into the realm where Kuiper Belt objects orbit in frozen silence, passes beyond where New Horizons spacecraft traveled during its journey to Pluto and the distant object Arakoth. The distance grows to 50 astronomical units, then 100, then 200 distances where even the Sun appears as merely a bright star, where the familiar planetary system shrinks to insignificance, where interstellar space begins asserting itself as the dominant environment. The transition back to interstellar conditions proceeds gradually. At several hundred astronomical units, the solar wind weakens as its density decreases with distance, eventually giving way to the interstellar medium's thin plasma. The Sun's gravitational influence remains measurable, technically infinite in range, but becomes progressively less relevant as other stars exert comparable forces across light-year distances. Galactic cosmic rays, partially deflected by the Sun's magnetic field in the inner heliosphere, penetrate more freely at these extreme distances where the heliosphere's protective effects diminish. The comet re-enters the radiation environment it experienced during millions of years of interstellar travel, resuming the slow cosmic ray processing that will continue indefinitely. The surface cools to equilibrium with the cosmic microwave background plus negligible stellar radiation. At approximately 2.7 Kelvin, molecular motion nearly ceases. The ice returns to the crystalline rigidity it maintained during the long crossing from its origin system. Any amorphous ice regions that survived previous processing crystallize fully at these temperatures given sufficient time. The nucleus becomes a frozen archive again, its chemistry suspended, its structure preserved until the next stellar encounter, if any millions or tens of millions of years hence. Only took a few months to traverse the planetary system, to briefly warm and sublimate and glow, to allow distant observers glimpses of its composition. Now the reverse journey begins. The climb back into darkness that mirrors the approach but leads nowhere familiar, points toward no specific destination, simply follows the hyperbolic trajectory wherever it leads. The velocity relative to the Sun approaches the asymptotic value that 15 kilometers per second characteristic of interstellar motion as the Sun's gravitational influence fades to negligibility. The comet's velocity vector deflected by 60 degrees during solar passage now points towards a different region of the galaxy than the direction from which it arrived. Where this new trajectory leads remains unknowable with precision. The galaxy rotates, stars drift through the spiral arms, gravitational perturbations from distant stellar encounters accumulate over millions of years. Tracing the comet's future path for more than a few million years becomes speculative, uncertainties compounding until predictions become meaningless. Perhaps 3I/Atlas will pass within a few light years of another star, receiving another gravitational deflection, possibly even capturing into orbit if geometry favours such an outcome. Perhaps it will wander for 100 million years without close stellar encounters, simply drifting through the interstellar medium, bombarded by cosmic rays, accumulating more radiation damage, aging slowly in the cold and dark. The comet carries forward its accumulated history, the composition inherited from its formation disk, the cosmic ray processing from millions of years of interstellar travel, the solar wind implantations and photochemical alterations from this solar passage, the gravitational deflection encoding the Sun's mass and position. These layers of information, some durable and some ephemeral, some readable and some degraded beyond interpretation, constitute the comet's archive. And the archive continues into darkness, into distances where human instruments cannot follow, into timescales that dwarf human civilization, into silence. The deep black reclaims what briefly entered our light. The observations end, the data remains. And somewhere beyond Neptune, beyond the heliopause, beyond the realm where our sun matters, 3I/Atlas continues. The darkness between stars holds no drama. No revelation awaits in the silence. No destination marks the journey's end. 3I/Atlas simply continues, velocity constant, trajectory determined, following the geometric inevitability of hyperbolic motion through space so empty that encounters approach impossibility. The comet does not know it travels. It does not measure distance or count years. It exists in the present tense of physics forces acting, atoms vibrating minimally in frozen lattices, cosmic rays occasionally disrupting molecular bonds without memory or anticipation, without past or future in any cognitive sense. The galaxy rotates around its center with patient slowness, completing one revolution every 225 million years. Stars drift through the spiral arms like slow-moving currents in an ocean of gravity and gas. The comet drifts with them, its motion negligible against these larger patterns, a single grain of sand moving through a vast sea. Occasionally, over millions of years, it passes relatively near another star within a light year, perhaps, or half a light year close enough for that star's gravity to nudge the trajectory by small fractions of a degree. These deflections accumulate, gradually erasing any connection between the comet's current path and its origin billions of years ago. The cosmic ray bombardment continues without pause. High-energy particles strike the surface, penetrate into the interior, break chemical bonds, create new molecules, slowly darken and process the outer layers, over 10 million years, over 100 million years. The radiation damage accumulates until the surface bears little resemblance to its original state. The solar signatures fade, first implanted hydrogen diffusing away, photochemical products erased by radiation, the processed rind from that brief warm period lost to cosmic ray gardening. Then deeper material ages, transforms, becomes something neither primordial nor recently processed, but simply old. Radiation-damaged ice carrying the marks of deep time. The temperature remains constant at 2.7 Kelvin. warmed only by the cosmic microwave background and negligible starlight. At such temperatures, time almost stops in a molecular sense. Chemical reactions that would proceed rapidly at higher temperatures freeze to imperceptibility. Diffusion slows to atomic scale creep. The comet ages geologically but not chemically. Its structure slowly altered by radiation, but its composition remaining largely frozen. Millions of years pass, indistinguishable from one another. The comet neither growing nor shrinking, neither warming nor cooling, simply persisting. Perhaps it encounters another stellar system. Perhaps, after 20 million years of travel, it approaches a red dwarf star, smaller and cooler than the Sun, its planets orbiting close where tidal forces lock them into synchronous rotation. The comet falls into this new gravity well, its trajectory bending, its surface warming slightly as stellar radiation increases. If the approach brings it close enough, sublimation might begin again. A brief coma forming. Observers on any planets in that system, if such exist, if they possess technology to notice seeing a faint visitor for interstellar space. Then it departs again, deflected onto a new path, continuing its eternal wandering. Or perhaps it never encounters another star. Perhaps it simply drifts through the interstellar medium for the galaxy's remaining lifetime, billions of years of unchanging cold, until stars themselves begin dying in numbers, until the Milky Way collides and merges with Andromeda in 4 billion years, until the universe ages beyond the era of star formation and even red dwarfs exhaust their fuel. The comet would outlast civilizations, outlast species, outlast worlds, simply by virtue of being frozen and inert and drifting through vacuum where nothing disturbs its slow decay. The human observations, the measurements and spectra and images exist as patterns of electrons in computer memory, patterns of ink on printed pages, patterns in minds that contemplate what those observations mean. These patterns will not outlast the comet. The computers will fail, the papers will decay, the minds will cease. The information extracted from 3I/Atlas's passage will fade back into entropy long before the comet itself disintegrates. Long before radiation damage and micrometeorite erosion reduce it to disconnected fragments. Long before those fragments themselves sublimate away in the faint radiation field of dying stars. But for now, for this brief moment in cosmic time, the knowledge persists. The composition is catalogued, the trajectory calculated, the comparisons made with solar system comets, the insights incorporated into models of planet formation and stellar system evolution. One more data point in the universe's vast information content, one more temporary correlation between states of matter that permits inference and understanding. Only took a few months of observation to extract meaning from millions of years of travel, to impose human significance on indifferent physics. The comet continues into darkness. The observations end, the silence resumes. And in the deep black between stars, where time moves slowly and nothing changes except through processes too gradual to notice, 3I/Atlas travels onward, frozen and ancient, carrying its secrets toward destinations unknown and perhaps unknowable. A messenger from one stellar system to none, a wanderer without purpose or path except what gravity dictates, continuing forever or until the universe itself forgets what comets are. The journey has no end. The story simply stops being told. Sleep well.